This lecture is part of an online series of lectures about modular forms, and it's the introductory lecture where I will explain roughly what a modular form is and try and explain why they're interesting. So first of all, we have the definition of a modular form, and the definition doesn't look very promising. It says that f of a tau plus b over c tau plus d is equal to c tau plus d to the k for some k times f of tau. Here a, b, c, d is a 2 by 2 matrix with integer coefficients with determinant 1. So SL2 means determinant 1. And this looks like, you can imagine you could write down dozens of similar definitions of a functional equation, and it's not at all clear why these should be of any particular interest. A special case when k equals 0 is called a modular function. So modular functions, which you might think are the simplest sorts of modular forms, are just invariant under this group action. So they look like that here. Tau is a complex number whose imaginary part is greater than 0. And f is sometimes holomorphic, although it doesn't really need to be. Well, the definition doesn't look terribly promising. Well, let's try and look at some examples. So I said the simplest case, let's take k equals 0. So what is the simplest example? Well, we could take a constant, but that's not very interesting. The simplest non-constant example looks like this. You write down this rather bizarre looking expression. Where sigma 3 of n is the sum of the cubes of the divisors of n, and that's not weird enough, so we cube it for no obvious reason, and then we divide it by some totally unrelated expression that looks like this. Here q, I should have said, was equal to e to the 2 pi I tau. So this really looks, it looks like someone had a competition where everyone was given 1 minute to think of the silliest possible definition of a function, and this was the winner. But what I want to show is that this really is a particularly natural and important function. In case you're wondering, this really is the simplest possible non-constant modular function. So let's see where it turns up. Well, I said that modular forms and functions had a curious habit of turning up in areas that seem to have nothing to do with modular functions. So the first area might be finite groups. And finite groups seem at first sight to have nothing to do with this funny functional equation in complex analysis. Well, when you classify finite simple groups, you find there are about 18 infinite families and 26 exceptions called the sporadic group. And the largest is called the monster group. This is really huge. It has about 10 to the 54 elements, and it lives in a space or in 196883 dimensions. In other words, it's the rotations of an object in this number of dimensions. So what does this have to do with modular functions? Well, let's take the modular function I mentioned earlier. So j of tau is equal to, well, we can write down a power series expansion of it like this. And it has all these weird coefficients, which are big and get bigger and bigger. And John Mackay had sort of moved from group theory to modular function theory at one time, and was rather surprised to notice this almost coincidence here. They're not quite the same, they differ by 1. And John Mackay told a few people about this and was told, this is a meaningless coincidence because finite simple groups have nothing to do with modular functions. They both have lots of big numbers in them, and just by chance a few of these big numbers are going to be the same. But it was soon noticed by Mackay and Thompson and Conway and Norton that it wasn't a coincidence. For instance, the monster simple group also lives in this number of dimensions, and the same with all the other coefficients of the elliptic modular function. So this is a typical example of what happens whenever modular functions turn up in some theory. All sorts of really bizarre coincidences start turning up. So here's this bizarre coincidence that these two unrelated numbers turn out to be almost the same. Another weird property of the elliptic modular function is that if you take the elliptic modular function of 1 plus root minus 163 over 2, this is actually an integer. And the integer is minus 262,537412640768000. Well, you may think this is some sort of special theorem that, you know, you could replace 163 by any other integer and then j of that would be an integer. Well, that's not true. If you replace 163 by almost any other integer, then j of that is not an integer at all. I mean, there are a couple of other cases which it happens, like 63 or 67 or 43 or whatever. But in general, you can replace that by an integer, and it's just some complicated number that's not an integer at all. This is related to another rather freaky coincidence, which is that if you take e to the pi root 163, this is 262,53741264077687439999999999925. So we've got this incredible list of nines at the end. This is very close to being an integer. If you notice, this number here is sort of pretty similar to that, except it's got a 743 there, which you may notice is rather similar to this 744 at the end. The explanation is that the reason why this is almost an integer is because this number is exactly an integer. In fact, if you look at this power series expansion, this is equal to q to the minus 1 plus 744 plus 196,884q, and so on, where q is equal to minus e to the pi root 163 if you put in this particular number of tau. And this q to the minus 1 is this almost integer here, and this term here is incredibly small. I mean, it looks huge because 196,884 is huge, but q is so tiny that this is very, very tiny. And if you sort of put this together and use the fact this is an integer, that shows that e to the pi root 163 is almost an integer. So this is part of something called the theory of complex multiplication. So what else is unrelated to modular functions? Well, how about sphere packing? So this is the problem of what's the densest possible way of packing spheres in n dimensions. And in 3 dimensions, this is an incredibly difficult problem solved a few years ago by Hales, who had this monstrously long computer proof of it. And in 4 dimensions, as far as we know, it's even worse. And 5, 6, and 7 dimensions, it's worse still. But in 8 dimensions, we know the answer. This was proved by Marina Wierzowska. And the densest possible sphere packing in 8 dimensions is actually quite easy to describe. You take all the points n1 up to n8 with the sum of the ni even, and all ni are integers, or all ni are integers plus a half. And these are the centres of the spheres. And this particular packing had been known for about a century. The difficulty was to show that it's the best possible. And Marina Wierzowska's proof of this involved a very complicated use of modular forms and depended on some absolutely extraordinary, bizarre coincidences going on. And a lot of cancellation had to miraculously happen in order for this proof to work. So why 8 dimensions? Well, we don't really know. There's a similar proof in 24 dimensions. The numbers 8 dimensions and 24 dimensions turn up a lot in the theory of modular forms, and we don't really know why. There are these 2 magical dimensions where all sorts of weird things happen. There's actually a simpler way in which modular forms turn up with this sphere packing. If you ask how many spheres are at a given distance from the origin, the answer turns out to be 240 sigma 3 of n, where the square root of 2n is the distance of the sphere from the origin. And if you look at this number 240 sigma 3 of n, you may notice that it's the same number that was turning up here in the definition of the elliptic modular function. So the elliptic modular function is somehow mysteriously related to this sphere packing in 8 dimensions. Where else do modular forms seem to have no connection with? Well, how about Fermat's last theorem? So it asks, are there any non-trivial solutions to a to the n plus b to the n equals c to the n with n greater than 2? And for many years, this was the most famous open problem in mathematics. And it was finally solved by Wiles. And the way it was solved is Frey noticed you could relate this to an elliptic curve, and particularly relate it to an elliptic curve y squared equals x minus a to the n, x plus b to the n. How he thought of this, I don't know. And Serre and Ribbett related this elliptic curve to a modular form. Or at least showed that if a certain conjecture about modular forms in elliptic curves was true, then this would imply Fermat's last theorem. And the connection is as follows. If you've got an elliptic curve looking something like this, then Wiles proved there's always a modular form associated to it. And let me sort of show why with an example. So if you look at y squared minus y equals x cubed minus x squared, then the number of solutions mod p to this is p minus cp for some constant p. And cp is the coefficient of q to the n in q times product of 1 minus q to the n squared times 1 minus q to the n, sorry, q to the 11n squared, which looks like this really bizarre infinite product. And this turns out to be a modular form. This is a really bizarre construction. You may wonder, how on earth did anybody think of going from an elliptic curve like this to a modular form? The answer is it took a long time for people to think of this and figure out what is going on. And what Wiles essentially proved is that if you've got any elliptic curve over the rationals, then there's a modular form associated to it. And what Frey and Serre and Ribbett proved is that if you have a modular form associated to this particular elliptic curve, then you get a contradiction. So Fermat's last theorem must be true. Wiles's proof of Fermat's last theorem is very closely related to the Langlands program, which is this huge program in number theory. It's probably the central research topic in number theory at the moment. And what it says is that Galway representations, this means you take the Galway group of the algebraic closure of the rationals over the rationals, you take a representation of that, so that's a map to GLN of some field, and these are very closely related to modular forms. Well, actually, they're related to something a little bit more general than modular forms called automorphic forms for a group GLN. So the modular forms are the case GL2. And the implication in this direction is very hard. And the implication in this direction is even harder. It's incredibly difficult to see why Galway representation should have anything whatsoever to do with modular forms. And what Wiles essentially did was he proved a very tiny little special case of this implication here, and that was already enough to prove Fermat's last theorem. Another special case of this is if you take n equals 1, which sort of looks trivial because it makes all the groups abelian, then this turns out to be class field theory, which was the sort of crown jewel of number theory. So what else? Well, how about the Riemann zeta function? So we've got zeta of s equals 1 over 1 to the s plus 1 over 2 to the s and so Well, at first sight, this seems to have nothing to do with modular forms, but Riemann pointed out that modular forms turn up here, because if we take pi to the minus s over 2 times gamma s over 2 times zeta s, this is equal to a half times the integral from 0 to infinity of theta of it times t to the s over 2 minus 1 dt. Well, actually I'm lying a bit, because there's a little bit of a problem with this inequality. So this is actually false. And the reason it's false is that this integral does not converge for any values of s. But that turns out doesn't really matter. We can, if it did converge for any value of s, it would give you this slightly modified form of the Riemann zeta function. You may ask, why did Riemann put these two terms in here? And the answer is he put them in because he was very clever and figured out what was going on. Anyway, this bit here is sum over all n of e to the n squared pi I t, and is a modular form, more or less. And Riemann deduced from properties of modular forms, if you put zeta star of s equal this, then Riemann noticed that the fact that this was a modular form implies the functional equation for the zeta function. And using this functional equation, he came up with the Riemann hypothesis, which says that all zeros of this function should have a real part equal to a half. Hardy was able to prove that it does at least have an infinite number of zeros with real part a half, and in order to prove this, Hardy again made heavy use of the fact this function here is a modular form. So modular forms are turning up very closely connected with the Riemann hypothesis, which is the probably the central open problem of number theory. For another example, let's look at the Jacobi or Jacobi triple product identity. So this says that if you take 1 minus qz plus z to the minus 1 plus q to the 4 z squared plus z to the minus 2 minus q to the 9 z cubed plus c to the minus 3 and so on, this is equal to the following infinite product: 1 minus qz, 1 minus qz to the minus 1, 1 minus q squared, 1 minus q cubed z, 1 minus q cubed z to the minus 1, 1 minus q to the 4, and you sort of keep on going like that. And it turns out that both sides of this are modular forms, at least if z is a root of unity. And provided you sort of add some minor fudge factors. They're both essentially modular forms. So one special case of this is if you look at the function 1 plus 2q plus 2q to the 4 plus 2q to the 9 and so on. This is equal to 1 plus q squared, 1 minus q squared, 1 plus q cubed squared, 1 minus q to the 4 and so on, where the signs keep alternating, the exponents alternate between 2 and 1. So modular forms turn up in these funny combinatorial identities. So I pointed out that the numerator of the funny identity defining the elliptic modular function turned up related to sphere packings, so we also ought to say something about the denominator. Well, if you look at the denominator, it looks like this. So we take q1 times product of 1 minus q to the n to the 24. And what happens if we expand this? Well, we get this funny series. It's 1 minus 24q squared plus 252q cubed minus 1452q to the 4 plus 4830q to the 5 minus 6048q to the 6. So it looks like a rather unpromising sequence of large integers with no obvious nice properties. And Ramanujan looked at this and he noticed that if you took the product of this number and this coefficient, we get this coefficient. So let's write this as sum of q to the n times tau of n, which is Ramanujan's notation. So Ramanujan noticed that tau of mn is equal to tau m times tau n whenever m and n are co-prime. Why on earth should this be so? I mean, this is again really bizarre, because if you replace 24 by almost any other number, you don't get anything like this. These coefficients really do behave rather more like, well, not quite random junk, but you don't get anything nearly as nice as this. You notice this is once again the magic number 24 turning up. So we'll be explaining why we get this rather bizarre equality. This turns out to be obtained by using something called Hecke operators, which are a really fundamental operation you can do with modular forms. Okay, so I guess that's more or less the end of the summary of weird things you can do with modular forms. I'll just say what we'll do in the next few lectures. The first problem that we want to solve is find all modular forms. Well, actually, we're going to find all the modular forms of level 1. So level 1 means we're using all matrices A, B, C, D in SL2 of Z, with so the determinant is equal to 1. And you may say, what's so special about this group? And the answer is there isn't anything particularly special about it. We can define modular forms for all sorts of other groups, but this is the easiest case, so it's what we're going to do first. Other topics we'll be covering are theta functions, which are related to the fact that you can count the number of spheres at a given distance from the origin in the E8 packing. We'll be covering Hecke operators, which were what you use to show that Ramanujan's tau function is multiplicative, and we'll be covering Eisenstein series, which are well, actually, this funny term here that you cube is the simplest non-trivial example of an Eisenstein series. So I'll just finish with another quote and a couple of suggested books. So there's a famous quote by Eichler which says that there are 5 fundamental operations in arithmetic: addition, subtraction, multiplication, division, and modular forms. It's not actually clear if Eichler said it, but everyone says he does, so whatever. And this quote sort of means that modular forms are a really fundamental branch of mathematics. They really do turn up everywhere in this really bizarre way. So I'll just finish by recommending a couple of books. The first is this book by Serre, A Course in Arithmetic, which doesn't sound like a terribly promising title, but arithmetic in French means number theory. And chapter 7 on modular forms gives a very concise and neat description of modular forms. And the first few lectures will be more or less doing the same topics as in Serre's book. One other classic I want to recommend is this one by Apostol on modular functions and Dirichlet series and number theory. And I actually got interested in modular forms because I found this book in a bookstore when I was younger and had no idea what it was about, but it sort of looked intriguing, so I bought it and then kind of got really blown away by it because, you know, here's one of the exercises of chapter 1. The exercise is to show this absolutely bizarre looking identity. So this is, it seems to me make no sense at all. It looks like one of these weird identities that Ramanujan used to like finding that nobody else could figure out how to prove. So if you don't know about modular forms, you just wouldn't have any idea how to approach this identity. If you do know about modular forms, this identity turns out to be quite easy. Okay, so that's the end of the introduction, and next lecture we'll be classifying or starting the classifying the level 1 forms.